Well, can we be sure that this algorithm works? Let's talk about a very quick proof of BFS. So our claim here is that BS finds all nodes that are connected to the start node. All right, so at the end of the BFS algorithm, our claim here is that V is marked found if there exists a path from S to V. And really all I'm going to say on this proof is that this is just a special case of that general algorithm we already proved by contradiction. If you wanted to do a more in-depth proof on this one, this would be a great practice for a loop invariant. You know, in fact, maybe I'll add that as a question on the homework assignment. That's a note for myself. It's a little bit more real world. You know, our loop doesn't just iterate for I equals I up to n. It's a little more complicated than that. But, you know, the proof by contradiction we had before will also work for this proof. All right, well, let's look at a slightly different way that we can use this breadth first search algorithm. So not just for finding all the vertices that are findable, but can we use it for computing what's called the shortest path? So determining the fewest number of hops between the start vertex and all other vertices. So for example, start vertex, a vertex A, a vertex B, and a vertex C. Maybe it's 1 hop to get to A, 2 hops to get from S to C, and then 3 hops to get to B, given this graph. But if I were to add an extra edge here, now we've reduced the number of hops to get to B from 3 to 1. So that's what I mean by the number of hops. Can we use breadth first search to find that number of hops? So this is question 1 on the next exercise. So the previous lecture slides, the exercise sheet ran over into this one, and now there are 2 questions just on breadth first search, and this is the first one. What additions do you need to make, or alterations do you need to make to this algorithm to make it compute the fewest number of hops? Okay, so we're going to have the same algorithm as before with these minor additions. First, we're going to initialize the distance to the start vertex, so that's the number of hops, the distance as 0. And we're going to initialize all of the distances to infinity. And if at the end of this algorithm we have something equal to infinity, we know it's because there was no path from the start vertex to that vertex. Now, when we're considering an edge from V to W, so we have a vertex S, that's our start vertex, maybe a vertex A, maybe a vertex W or V, and another one W. So there's some path to V at this point. Now, when we consider this vertex V to W, if W is not found, then we're going to set the path length to W equal to whatever the path length was to V plus 1. And the 1 comes from this vertex here. So let's look at that in code. The only additions here are highlighted. We mark all distances as infinity except for the start vertex. And we update, whenever we add something to the queue, we update the length to its, the path length to itself. So for example, since we've already gone through this with breadth first search, let's quickly just annotate this graph with the distances. We start out at S, it has a distance to 0. When we add A to the queue, when we're looking at this edge here, when we add A to the queue, it's equal to 0 plus 1. So that 0 comes from there. Same thing for B. 0 plus 1 is equal to 1 is equal to 1. That's where the 0 comes from. So we've done both of those edges. Now if we pop A off and we look at this edge to C, it's going to be 1 plus 1 is equal to 2, where, you know, this 1 comes from here. And again, the second plus 1 here, in all cases, is just because we have to take the current edge to get to that vertex. When we pop B off, we'll find that D is 1 plus 1 for the same reasons, and then eventually E will be 2 plus 1. And usually I have this as coming from C. So another way to think about this is A and B are in the first shell away from the start vertex. C and D are in the second shell. They're both 2 hops away. And E is in the third shell away from the start vertex.